Okay, whoops, there you go. Okay, so now we're going to review energy, which again is going to be the biggest chunk of the test. I'd really recommend put a lot of your focus on here, making sure you have kind of all the ins and outs of this. I'm just going to do a very quick overview, and like I said, we'll come back and do a couple practice problems together afterwards. So energy in general, I know this definition doesn't help us out too much if we don't remember what work is, but energy is the ability of an object to do work, and we're going to talk more about that later. We're first going to go through types of energy, and then we'll come back to this concept of doing work and what that means. So these are the main types of energy. Just to review, kinetic, again, comes from the object's motion, right? Anything kinetic means we're moving. So as an object is moving, it has kinetic energy. If an object is at rest, it doesn't have kinetic energy. And again, that's our formula, K, or sometimes it's Ke. That's 1/2 m mass times velocity squared. Now, energy, I should have said here, energy is a scalar. The reason why is because it's not a direction of energy, I guess we could say. Even if you use v for velocity, what ends up happening is that it gets squared. And so if it was a negative direction, it ends up becoming positive anyways, and we lose the essence of the direction. So energy is a scalar. It doesn't really tell us a direction. We have gravitational potential, which is energy stored in an object due to its height. We're going to talk about this in this question that we're going to do here, but we cannot really say that an object by itself has potential energy. I don't really say that my phone has potential energy while I'm holding it up here. What we say is the object Earth system, the phone Earth system, does have potential energy stored in itself. If I'm focusing on just my phone here, it doesn't have potential energy. I have to say phone and Earth system has potential energy because potential energy only comes from in reference to a zero level, right? So we have to be aware of we're referencing whatever that ground level is. The formula for this, don't forget that potential energy was U and not P. P is for power, I guess, so maybe that's why they used U. But this is potential gravitational mass times G, which is 10 times height, mgh. Now we can also have spring potential, which is the stored energy of a spring when it's extended or compressed, depending on how that spring works. Some springs extend, some springs compress. And this was US, so that's spring potential. That's again 1/2 K times x squared. So don't forget that K was the spring constant. Just for whatever that spring is, there's a certain constant that defines it, depending on how rigid the spring is, how big and all of that, all those factors go into it. And then x was the distance compressed or extended from an equilibrium. So you'll just want to remember those variables, spring constant and then the distance compressed. Thermal energy is shown as E thermal, which is the dissipated energy due to heat or friction. This is, I want to actually write here, this, if it's due to just friction, rubbing up against something, this equals force of friction times D. The reason why is FD is the formula for work, if we can remember that. And since energy is the ability of an object to do work, the thermal energy is the work done by friction. Again, we're going to come back to work in just a little bit there. So if you want to write that down, force of friction times the distance traveled. So if I have my calculator traveling across my hand, that distance traveled is the length of my hand, right? And then whatever force of friction is going on between my hand and the calculator. So those are the main types of energies. Now we can talk as well about some more general types, which is mechanical energy, which is the sum of an object's kinetic and potential, including gravitational and spring if applicable. Obviously, sometimes spring does not apply. But if it does, then yeah, we would add that into an object's mechanical energy. Now again, that means, I should clarify here, a system's, let's cross that if I can, a system's Because again, you cannot have gravitational potential energy without talking about the system of the object in the earth, right? Now we know that energy is conserved, meaning it can't just be created out of thin air. Yeah, my phone's not suddenly going to spontaneously combust out of thin air. Yeah, some outside force may cause it to, but that is because it would transfer energy to my phone if it was hit by a laser beam or something. Yeah, sure. Then energy is being transferred into my phone and then it spontaneously combusts. But it's not going to happen on its own. That's why we say energy is conserved. However, energy can be dissipated due to heat and friction. We know that when we rub our hands, we feel that heat warming up. So again, if I were to roll a ball, if I were to roll a car or something like that, some of that energy is going to get lost to heat and friction. But it's still conserved. Again, the loss has a reason. The reason is that contact, right? So it's not just magically disappearing out of thin air. Because of that contact, that's why the energy is dissipating. So we say that total energy is constant, meaning that the sum of all the energies is the same throughout an object's motion. Again, that's because if we add in that dissipated energy, that would equal the same thing throughout the entire thing of an object's motion, the entire time of it. Adding in any dissipated energy, yes, all that energy is going to be the same because, again, we can't just magically create energy. Whatever energy an object has to start with, it's going to have all of that energy throughout until it stops its motion. So if there's no friction, we can also say the mechanical energy is constant because, again, friction can dissipate some of that mechanical energy, but if there's no friction, then mechanical energy is going to stay the same as well because there's no outside force or outside object or whatever taking away energy from that system. So that's just a real quick overview of energy. Let's go ahead and look at this one problem here before we go back to talking about work. So again, I've tried to emphasize here, I feel like I didn't do a very good job of this when I taught you guys the first time. Energy of a system versus energy of an object. Like I said, with gravitational potential energy, we really have to say a system has potential energy or gravitational potential energy. I cannot really just say, oh, this phone has gravitational potential. I would say the phone Earth system. So when you're doing these problems, you really have to focus on, are they talking about the system of an object and the Earth? Or are they just talking about the object by itself? So, for example, a box starts with initial speed and slides from one platform to another higher platform. So it does make it all the way up and over. Yeah, it ends up over here. Assume that frictional forces and air resistance are negligible. This is always very important to keep an eye out for. Super duper important to notice if it says friction doesn't matter, or if it says it's a rough surface, that means friction does matter, right? For the system consisting of the mass and the Earth, hey, they are talking about a system here. So what can we talk about if it's a system? We can talk about potential energy, gravitational potential energy. We can't talk about that if we're not talking about a system that includes the Earth. So it says, what happens to the total mechanical energy of the system? So thinking this through, total mechanical energy is all of the energies present. Now, because this box is in motion, and because we are talking about the system consisting of the mass and the Earth, what energies are at play here? We listed them all out here. What mechanical energy is going to be at play here? Well, we're going to have kinetic energy. This is the total mechanical. We're going to have mechanical. Ugh, it looks like maniacal, whatever. We're going to have kinetic because the object is in motion. And we're going to have potential gravitational because we're talking about a system. Now, do we have any thermal energy being dissipated here? Is there going to be any thermal energy lost? No, because it says friction is negligible. So, because there is no friction, these two are going to remain, for Pete's sake, constant. There's not going to be any energy lost to friction. Yeah. So those are going to remain constant. So looking at our options here, what's our answer then? C. It remains constant because there is no friction. The kinetic plus the gravitational potential, yep, that's going to remain the same throughout. Now, let's erase this real quick. What if we only looked at the system consisting of only the box? Now, because it's only the box, the total energy of just the box, total mechanical energy of just the box. Are we able to talk about gravitational potential now that we're talking about just the box? No, we're not able to talk about that if that's the only thing in there. Again, gravitational potential energy only exists in reference to the Earth. So there's no friction, but it's just kinetic now, right? That's it. We can't talk about potential energy because we're not talking about the Earth. So think about this then. If this question asks, what about the box by itself? Think about, again, what is the formula for kinetic energy? We got 1/2 mass times its speed squared. So kinetic energy is dependent on the speed of the object. Think about how the speed of this is going to change. There's no friction, but it is gonna do something here. It's gonna do something here. We know how this works. So think about just the speed of this object as it goes through. And then look at your options and see if you can tell, okay, what would happen to just the kinetic energy? Because that's all we can talk about if we're only talking about the box. Is it going to increase for the entire trip? Is it going to first decrease, then increase, remain constant, or increase, then decrease? Again, think about what happens with the speed. That's going to be our answer here, because that's going to directly translate into the change of kinetic energy. The change of the speed directly translates to the change of the kinetic energy. Well, there's no friction, so going on a flat surface, that speed is constant right there, but this is going to increase speed, right? Yes, of course, we are only talking about the box, but gravity is still a thing. We're not really including gravity in the system, we should say. We're not including Earth in the system, but gravity is still acting on it. So it is going to speed up here. And then as it goes up, did I say gravity's going to, the box is going to speed up here. As it travels up, it's going to decrease, right? Because gravity is pulling down on it. We're not talking about the energy it has from gravitational potential, but again, gravity is still going to work on it. So you should have said first increases, then decreases. It's going to increase and then decrease. It's going to remain constant there because there's no friction. But so be very careful again as you're talking about energy. They are going to be very specific about if it's a system of including the Earth or not. If it does not include the Earth, you cannot talk about gravitational potential energy. Let's go ahead and go on to work. So this is still within the umbrella of energy because energy is, again, the definition of an object to do work. The definition of an object. The ability of an object to do work. So we define work as the transfer of energy from one object or system to another. Because again, my phone right now, if I'm talking about the phone Earth system, it has some potential energy. Yeah, it's not going to, again, spontaneously combust. It's not going to spontaneously move because there's no outside forces working on it. There's no outside forces to transfer energy to it. However, when I push it, I am transferring energy to my phone because, in fact, I'm transferring kinetic energy to it because it's moving. So I am doing work on my phone, and that's actually what it says here. This is how we talk about it, right? If a person lifts a box that would give it 10 joules of gravitational potential energy, then we can say the person did 10 joules of work on the box, as that box now has 10 joules more of mechanical energy, right? Again, if I have my phone here, if I have the phone Earth system, yeah, if I lift it higher, I am transferring more potential energy to the phone Earth system by doing that lifting, right? I did work to lift that phone, and the work I did transferred more potential energy to my phone. So I did the work, which transferred energy to my phone. Now, what we find out is that the net work done on an object, now again, backtracking here, on an object, not a system. Yes, the reason why I'm saying this is because the network equals the change in kinetic energy. You'll see this W net equals change in kinetic. That's because we're talking about the work done on an object, not on a system. So we're not talking about potential energy here. If they are referencing a system, you would not necessarily use this work energy theorem in the same way. It's talking about just any work done on an object by itself. So looking at this problem, we're going to apply this in the next problem, and then we're going to come back and work through a couple other problems together. Network equals change in kinetic energy. So looking at this example, it says a 4 kilogram box starts with a velocity of 6 meters per second to the left. So we always want to draw out a picture and label our directions. So to the left. It's up to you. It doesn't matter. The math will work out. However, we typically say the left as negative, right? So negative 6 meters per second. It says the net amount of work is done on the box, and the box is now moving with a velocity of 4 meters per second to the right. So here's where it ends up. 4 meters per second to the right. What was a possible amount of net work done on the box? So, well, they're helping us out here. Net work tells us, oh, hey, this is the work energy theorem because that's related to net work, and not only that, but net work equals the change in kinetic energy. And we definitely have a change in kinetic energy here because the box is changing directions and speeds. So we just need to figure out what was this change in kinetic energy to figure out what the network was. So do you guys remember change in K? What would I expand that to? I'm subtracting two things to get a change. Do you remember what it was? That's K final minus K initial. That tells us the change in K, where it ended up minus where it started. So from here, we're going to do some replacing again. Let's go ahead and write that out, replacing with the formulas. But what we want to be careful about is when we replace with the formulas, we want to make sure that we're writing, we're keeping the subscript for F and I on the speeds. So write it out, replacing with the formula for kinetic energy. If you're not sure what I'm talking about, we'll just tack it on here. So you should look back to what you'd written down so far. This is 1/2 mv. What I wanted to say here, final squared. Because again, this kinetic energy is going to be based off the final speed minus this kinetic energy is based off of the initial speed. And do not forget that square there. So all we got to do is kind of plug in from here. We have the initial and we have the final. Be careful not to jumble those up. Go ahead and plug in and see what you get. Okay, so we have 1/2. The mass is 4 kilograms up there. B final is positive 4 squared minus 1/2. Mass is 4 once again. B initial was negative 6 squared. So if we go to a calculator to do this, we should get negative 40 joules. That makes sense because we are changing direction from where we started. So a negative work just tells us that we are changing direction. Yeah, it doesn't necessarily tell us which direction, but a negative amount of work does tell us that we are changing direction. Doesn't necessarily tell us which, though. So once again, that was a very, very quick overview of energy and work. We're going to come back together and work through a couple more problems before we go on to our last section.